The fourth type of sequence container is array. Now, an array STL container not only requires a type for each element, but also requires you to specify the size of the array as an additional dimension parameter in the array type. And arrays are very inflexible. The STL array type is not particularly more friendly or more flexible than the ordinary C++ arrays that you can declare using square brackets. You have no ability to do inserting and deleting. There is no pushback. There is no push front. You do have very efficient random access, and by using the array STL class as opposed to the ordinary built-in kinds of arrays, you can make use of all the conventional iterator syntax. You can increment iterators both forward and backward, and you have access to all of the algorithms that are provided as part of the STL library. Finally, the fifth sequence container is the forward list. This is a singly linked list. It was introduced in C++11 to be a more memory efficient form of list than the plain list, which is a doubly linked list. The upside of forward list is that it uses the minimum amount of memory possible for containing an arbitrarily long sequence of data where you only need to have efficient insert and deletion at the front. Okay? So there is a push front for the forward list, but there is no push back. Also, with your iterator, you can only go forward through the list. You cannot go backwards. So whereas vectors and decs have what are called random access iterators, supporting subscripting with square brackets, as well as ++ to go forward and -- to go backwards, and list is bidirectional, that is, you don't have subscripting, but you do have both ++ and -. Forward list has what's called forward-only iterators. You can only move the iterator forward, you cannot move the iterator backward, and you cannot do any subscripting. In terms of how these things might look in memory, here are some diagrams. A vector stores values in ascending contiguous memory locations, and it's inexpensive to insert and delete things at the end of a vector. A double-ended queue is not guaranteed to store elements in ascending contiguous memory locations, but it does give you subscripting, and it does give you the ability to efficiently put things at the beginning and the end of the deck. A list makes it very convenient to traverse forward and backward and to insert and delete things anywhere. An array is extremely efficient in terms of accessing a sequence of elements in contiguous memory, but where you have no flexibility at all over changing the size of the array. And then finally, a forward list only makes it cheap to do insertions and deletions at the beginning. So that's the sequence containers. Now the associative containers store elements in sorted order, and virtually always this involves using something like a red-black tree or some similar kind of tree structure that guarantees log-in lookup performance. By default, the associative containers store elements in ascending order according to how the less than operator works for the particular type of element being stored. There are 4 standard associative containers. In a set, we're able to store single values, and duplicates are not allowed. So this is the same as a mathematical set. You can store as many items as you would like in the set, but no duplicates will be allowed. As I said, doing a lookup or an insert is guaranteed to be order log n. Iterators are bidirectional. We can traverse through a set either forward or backward using ++ and -. Now, one side effect of the fact that an associative container is sorted is that iterators are all treated as though they point to const values. If you're using an iterator to step through the elements of a set, and at some point you said something like star of the iterator gets 19, to change the value of the thing that you're currently pointing to with your iterator to 19, well, that probably will destroy the sorting order of the set. So you're not allowed to modify a value that an iterator is currently pointing to when you step through a set. A multiset is like a set, except duplicates are allowed in a multiset. So you could think of a multiset as being like a bag of objects kept in sorted order. So if you had a multiset of marbles, for example, you might have 4 blue ones and 8 red ones and 3 black ones. Here on slide 18 are some illustrations of set versus multiset. The set here is shown as the balanced binary search tree. The multiset is also balanced, but notice that we have multiple 5s and multiple 6s in our multiset. So really, a multiset is like the very first binary search tree that we developed, where we didn't worry about whether we did or didn't have duplicate values in the tree. And then a set is what we modified that into by adding additional logic to make sure that multiple occurrences of the same value were not inserted into the binary search tree. In addition to set and multiset, which store individual element values, we have map and multi-map that store pairs of values. That is, we think of the first value as being like a key, and the second value as being a value that that key is associated with. The rule for map is that no duplicate keys are allowed. For the different keys, you may have the same value occur several times, but it's guaranteed that the keys will be unique in a map. Here on slide 20, we have a map in which the keys are ints and the values are chars, and you'll notice that the key 5 only exists one time, but it's associated with the value a, and 2 is also associated with the value a, that is the character a. Similarly, the key 4 only occurs one time, and the key 8 only occurs one time, but each of those keys is associated with the char value x. As with the set, a map guarantees that lookup or insert is order log n. As with the set, we can do bidirectional iteration through the map. That is, we can go forward through the map in ascending order by key, or backward through the map in descending order by key. And as we talked about with the set, the keys in a map, because the keys are used for sorting the pairs of values, are treated as const. Now the values associated with those keys, on the other hand, are typically modifiable. The difference between a map and a multi-map is that in a multi-map, a key may occur multiple times. So here we have a key of 5 associated with the character a, and here we have a key of 5 associated with the character x. How might this ever occur? Well, imagine that the key is like a customer ID number, and the value associated with that key is a particular buy or sell order submitted by that customer. In this multi-map, we're maintaining all of the information in customer order, but we have different buy and sell orders for each customer. So for quite a long time, standard C++ only provided sequence containers and associative containers. In C++ 11, unordered containers, or hash tables, were also added. In an unordered set, we're able to store single values with no duplicates. And we do have the ability to traverse through all of the elements in a hash table one at a time using the ++. But since a hash table or an unordered set is not sorted in any sense, these values will be presented in what may appear to be a random order, and there's no -- provided for the iterator so that you could go in a backwards random order, which is sort of a bizarre idea. Okay, so in the case of an unordered set, when we ask for the begin iterator, that gives us an iterator to a value, and we can keep incrementing that iterator to get to other values contained within the unordered set until we run out of values, at which point the iterator, after we increment it, will be equal to the end iterator. But there's no sense of these values being ordered in any way, and so we can't use -- to start going back in reverse through the unordered set. An unordered multiset is like an unordered set, except that you are allowed to have duplicate values.